Okay, welcome back. You're here at the 2018 Earth Engine User Summit. My name is Tyler Erickson. I'm a developer advocate on the Earth Engine team. I'm doing a little of the emceeing today, and it is my proud privilege to be able to introduce our plenary speaker, Rebecca Moore. Rebecca is the director of all things Earth at Google, the Earthlings. So she does Earth Outreach, Earth Engine, and the New Earth. And she is going to give us a little history of Earth Engine, a project that she helped start about 10 years ago. Welcome to the stage, please.
Thank you, Tyler. Good morning, everyone, from in Dublin. And good evening, good afternoon, good night, everyone on the live stream. It's really exciting. Our team looks forward to this event. This is like our major event every year. It's something that we plan for. We drive the software engineering team to get new features ready for. So it's very exciting for us that we're all gathered here today. I'm just curious, I always like to have a feeling, for how many of you is this the first time you've ever attended? Okay. And the converse, I just like to see how many of you have been here before, have attended an Earth Engine User Summit. All right, good. So there's a number of new folks, and so what I like to do is help you drink our Kool-Aid. Because we are very passionate. You could probably tell just even from the early communications about this whole event that our team is super passionate about what we do. And we call ourselves Earthlings, but we also call ourselves Geo for Good. We're sort of the philanthropic arm of the Google Earth and Maps team. And our focus is on empowering everyone around the world with our tools and data to make the world a better place, to create positive change in the world. And Earth Engine is very much in that spirit. Going back to, again, the history of all this, before Earth Engine was born, the Google Earth Outreach program was born, and it was a very small beginning, a humble beginning, which was that I live in the Santa Cruz Mountains, about half an hour from Google. There actually is the largest stand of old-growth redwoods in Santa Clara County near us. And one day in the mail, I got a notice that with a black and white, sketchy, grainy map, the upper right there, saying notice of intent to harvest timber. And it was kind of concerning to everyone in the community, but no one could read the map. And so meanwhile, 2 months earlier, Google Earth had launched in June of 2005. And I thought, well, maybe we could better understand what they're proposing in this plan if I studied it and remapped the elements of the plan against the high-resolution satellite imagery and 3D terrain and created kind of a navigated tour and story of what they're proposing. And when I did that over a weekend, it was shocking how much you could understand about the proposal that was not obvious from the 200-page document and sketchy map. And ultimately, it mobilized the community, it garnered political support, and we used Google Earth actually to prove the plan was illegal, and we stopped the plan. We saved 1,000 acres of redwood trees, and now that land is going to be permanently protected as open space. So, yay! So that's one point for the good guys. And the lesson from that for us was seeing is believing, right? You can understand complex issues sometimes when you can portray them on this kind of high-resolution imagery canvas. But that's not enough. Now let's look at this video of those of you who know the historical imagery feature in Google Earth. You can go back in time, and we're looking at deforestation in the Brazilian Amazon over a period of about 20 years, a very characteristic pattern of deforestation. You can see in the satellite imagery in Google Earth, all over the planet, you can see evidence of tremendous transformation of the landscape. Not all of it good, not all of it sustainable, and it's visible from space. But seeing it is not enough. And so when we were actually there in the Amazon doing some training for some indigenous communities on using Google Earth, some scientists approached us, geoscientists, and said, look, we love Google Earth, we love Google Maps, we can get from point A to point B, we can look at our neighbor's backyard from space, that's all fine. But what we really want to be able to do is map and measure and monitor this changing surface of the planet. And in fact, particularly in the Amazon, we're losing 1 million acres a year to deforestation, a lot of it not legal, happening in remote places where there was not good law enforcement on the ground. And as these geoscientists explained, you could have a virtual alerting system based on the data that was collected every day. But the problem was it was a brutal amount of data, terabytes or petabytes of data. By the time they would download it, run the analysis on a single computer, it was too late. The results were often irrelevant because it took weeks to do that. So that was the pitch to us. Google, you have the imagery, you're letting us look at it. Why not let us do science, actually measure and monitor at scale? So that's where Earth Engine was born, really, in the Brazilian Amazon. And we launched in 2010 at the Copenhagen International Climate Conference with a focus initially on forest monitoring, and you'll hear more about that. But that is our most sort of mature application area for Earth Engine, although there are many, many more now. So we view Earth Engine as Google's cloud platform because we've been built from the ground up to run in the cloud at scale for easy petabyte scale analysis, and again, emphasize the word easy, on satellite imagery and other geospatial data. Well, there's a lot of data out there, and that's why this is needed. NASA and USGS alone have many, many missions. A number of these are collecting terabytes of imagery a day. It can end up being petabytes per year, and that's very difficult for ordinary mortals to manage if they want to access that data. The European Commission, European Space Agency, has launched, and many of you know, an incredibly ambitious and very successful to date series of missions, the Copernicus program, the Sentinel sensors, that are systematically observing land, ocean, and atmosphere, and they are scheduled out to 2030. Amazing data. And these data sets, and again, you guys, many of you are experts, you know this. This is not just pretty pictures of the planet with RGB pixels. This is often multispectral data. It may be maybe floating point. There's a scientific resolution to the data, and it's important for any system to be able to faithfully store the full scientific integrity of this data. So that was a requirement for Earth Engine. And again, just looking at Landsat, there's more than 6 million of these images going back, 46 years of the archive. But the data that's being collected by many of these government satellites tends to go onto tapes, very secure tapes. In this case, at the USGS Aeros Data Center in South Dakota, fantastic secure storage, but not online, not on spinning disk, not that accessible. And that was the challenge that was presented to us. And so when you look at it, really this was an insight from the late Jim Gray of Microsoft. Often it turns out to be more efficient to move the questions than to move the data. That is, instead of making everybody around the planet download terabytes or petabytes of data and build server clusters to do the processing, why not have the data housed in the cloud and move your algorithms and questions there and make it simpler for everyone? So that is what we've done with Earth Engine. The principal kind of breakthrough is to co-locate this big public data and also your private data if you want to upload your own data. Massive scale of parallel computation, access to tens of thousands or hundreds of thousands of computers, and then being able to run your own algorithms in that context. It's customized for geospatial data, and we've got an Earth Engine API to let you build your algorithms. So it took us about 3 years to get all that data off tape from USGS. Thank you to Tom Loveland and Eros Data Center for working with us to get it all off tape and online so we could put it in the hands of the entire scientific community. When we had all these images, we kind of started poking around with it ourselves. And this is a typical satellite image, as many of you know. Often they're cloudy. And in the era of scientists downloading scenes and doing analysis on a scene, if a scene was very cloudy, people couldn't use that scene. But in the Earth Engine model, we just store all the pixels, and we let you sift through those pixels looking for the best, least cloudy, for example. If you want instance of each pixel, you can take a set of images like this, clouds move around and so on, and you can composite something like this. This is the Isle of Mull in England. It never actually looks like this. But every pixel in there is legitimate. We applied this ourselves at global scale. In 2013, we sifted through all the Landsat pixels, and we produced a 15-meter cloud-free resolution satellite imagery base map for Google Earth and Google Maps. And that's what you see when you open it up. And you can zoom in very far into this. When we did this, finally my boss said, OK, Earth Engine may be useful after all. Because we had now decades, 3 decades, more than 3 decades of the Landsat archive, we applied that technique because we were curious about what would it look like to see the changing planet year over year over year. We created one of those cloud-free composite images of the Earth at 30-meter resolution for every year from 1984 to 2016, and stitched it together into a zoomable, browsable experience that we call time-lapse. When you do that, you can see just amazing phenomena. You can go anywhere, but for example, Las Vegas, you can see, was the fastest growing city in the US, and while Las Vegas is growing, you can see Lake Mead shrinking. That's interesting. Again, something you can grasp in a few seconds. I love this one because while you can see the human footprint on the planet in terms of things like urbanization, you can also see beautiful geologic processes that unfold in this time scale over years. So here we're looking at sedimentary activity off the coast of Cape Cod, where the sands are shifting south over a period of decades. You can see river meanderings. This is in Tibet. And in fact, geomorphologists have done studies using time-lapse, studying river morphology and finding new insights that kind of contradict previously held wisdom about river geomorphology. We launched time-lapse originally in 2013 with Time magazine, and then we updated in 2016. The point here about scale is it was 5 million Landsat images that we analyzed, 32 years of the archive. It was 3 quadrillion pixels to sift through and create those mosaics. It required more than 2 million hours of computation, but because we ran it on 66,000 computers in parallel, we had the result in a couple of days, whereas on a single computer, it would have taken 300 years to produce time-lapse. So it becomes more clear why it hadn't been done before. All right, so those are visualizations, but again, we built it for science. We built it to put in the hands of people like you. And the first real breakthrough scientific result came in 2013 when Matt Hansen of University of Maryland produced the first Landsat-scale global high-resolution map of forest cover loss and change, loss, gain, and change. And that was published in Science magazine, again in 2013. And before that, I think we didn't have street cred, I would say, with the scientific community. I think there was some question, what is this Earth Engine thing? Is it a toy? Can you actually do something useful with it? But Matt Hansen, he's sort of my hero because he took a chance in terms of moving his methodology onto the Earth Engine platform when it was much more primitive and nascent than it is now, and produced this amazing scientific result. This was 1 million hours of computation. We ran it on 10,000 computers in parallel. It took, again, a few days. It would have taken 15 years on a single computer to produce that global data set of forest cover and change. It's up to almost 3,000 citations now. There have been incredible follow-on derivative studies done using that data set as a foundation. Also importantly, I wanted to mention what it would have cost in Landsat data if the USGS and NASA had not had enlightened data policy in 2008 when they changed the cost of Landsat from $600 a scene to free. That was the real change that suddenly made the need for cloud computing apparent. Because, as Matt Hansen said, it used to be for doing these scientific studies, he would use the data he could afford, not the data that he actually needed. But now you could access all the data. So yeah, that would have been almost $400 million worth of data. So obviously that study would never have happened. So kudos to NASA and USGS for making Landsat free. And let's keep it that way. Excuse me. All right. So when that came out, there was a lot of global attention around the world. This is just one example in the New York Times. More importantly, one of the real goals of Earth Engine is we see that technology can be a bridge from science to society. That, traditionally scientists may do their work in a lab, on their lab computer, get a result, publish that, but it's difficult for them to share the data. It's difficult for them to make their science open, to share their methodology. And so if they want to turn it into, let's say, an operational application that can be used by decision makers, making that transition, that leap, is really difficult. And that's what we've tried to facilitate with Earth Engine, because the data's all in the cloud, your methods are in the cloud. It can be simple, relatively, to now turn your scientific capabilities over to audiences who may want to do something impactful in terms of decision-making on the ground. So in this case, Global Forest Watch was built by WRI, leveraging these data sets and leveraging Earth Engine, and putting this information about forest change into the hands of decision makers on the ground. Okay, so that's kind of the history. So for those of you who've been here before, now you get some new stuff. And some people think of time in like calendar time or fiscal years, but like we think in terms of Earth Engine User Summit years. So we were trying to reflect on the team, what's been launched, what's happened, notably things we've done, but more importantly, things the community has done in the last year since we had all gathered, in June 2017. So I wanted to just kind of go through that. A few things. Last year, we signaled that there was a paper finally coming out. For years, you guys have been asking us, please give us a paper we can cite. When we use Earth Engine in our research and we get a paper accepted, we want to be able to have a reference, but we don't have anything. So we did publish our kind of seminal paper on Earth Engine in Remote Sensing the Environment last July. That's the paper you should cite. It's open access, so it's free to download. It's actually been the most popular download for months. So encourage you to read that, and that's your citation. One of the big values of Earth Engine is that we do carefully curate a high-quality public data catalog. That it's, while we're sitting here, there's thousands of images and scenes streaming into Earth Engine, coming from Sentinel, Landsat, and so on. And in the last year, we've added a bunch of new data sets. You guys vote on the ones that are most important. That's what drives what we prioritize. There's a lot of data out there, but some of it's more useful than others. So One of the most important ones is the Landsat Collection 1 surface reflectance. I'm curious how many people have discovered that and are using it. Yes, okay. So I assume you're happy about that. Really a key launch. The Forma 250-meter daily deforestation, that's based on MODIS, that was launched. Here we're zooming in, you're seeing a snippet of that. NASA, the ocean color data from CWIFs. This is important for understanding the health of coastal ocean ecosystems. The PRISM climate data set, that was very, very highly requested. That's now out. The global administrative unit layer, this is country and subnational boundary data, is about to come out. This is the one that didn't squeak over the finish line, but it should be coming out very soon. JAXA, over the past year, we really strengthened a wonderful partnership with the Japanese Space Agency, and they have also an incredible set of satellites and missions going on. And so we recently launched the ALOS Global 30-meter DSM, the AVNIR data set, and the PALSAR-derived forest, non-forest map. One thing I wanted to point out is we are always gratified when we publish a new data set, we immediately see the community take it up and use it, and this is an example. The JAXA 30-meter DSM is actually quite good. It's derived from their 5-meter commercial data, and they downsample it to 30. So it's quite accurate and was preferred in a recent paper that came out on estimating urban agriculture services as compared to using the SRTM 30. Global Fishing Watch, I'm not sure how many of you know about this amazing project, but it is getting daily AIS and VMS ship location information and using that to derive where fishing is happening and what kind of fishing, and is it happening in the right places or not in the right places. And that data set is now in Earth Engine. There is, and this has really been encouraging to see, there's a whole research community spinning up around that data of scientists, of economists, of policy people, because having that treasure trove of data is now unlocking not just stories that are in that data, but really fundamentally understanding the nature of fishing. 20% of the seafood caught is actually illegal, but it's everything that's been going on the high seas has not been known until now, and this data is public, open, free, and this community of scientists are deriving a number of interesting results from this. A few months ago, they published a paper in Science on tracking the global footprint of fisheries, actually showing this globally. Just some praise from the press on this importance of technologists working with the development community and scientists to unlock some of these key data sets that help us understand the planet and how we are living on the planet. This is an image of 1 year summarized of fishing activity from that paper. Now, this one's very interesting. In Earth Engine, and one of the most exciting areas we're seeing is people accessing not just one data set, but multiple data sets and fusing them together, because it's very easy to do that in Earth Engine. All the data is at your fingertips, multiple different data sets, and deriving some new insights from bringing those together. So in this case, we have sea surface temperature data, and now bringing in the Global Fishing Watch data, you can start to look for patterns in fishing compared to water temperature. If we zoom in, if you look at these white squiggle lines, these are fishing boats, and you can see that as the water is, I think it's as it's warming, or cooling, I guess, the boats are tracking that temperature gradient. Very, very fascinating. So this kind of study is being done in Earth Engine, could be done by any of you as well. Completely different study was published in Nature a few months ago by Dan Weiss and team from University of Oxford, together with the Joint Research Center, looking at creating a global map of accessibility to cities. So basically, they brought in a lot of different data sets, road networks, other networks that describe difficulty of getting from, or how you would move from point A to point B, creating essentially a friction surface from every point on Earth to other points. How hard or easy is it to get there? And then over that, looking at measuring the difficulty or the accessibility from any point to the nearest city. Why is this important? Well, I mean, this is often how people get access to health resources, how they get access to jobs, understanding, and also conversely, when remote areas are made more accessible with road building, it can lead to unsustainable extraction. So having a better global picture of that has been quite important. And that data is in Earth Engine, and you can use it to derive other kinds of knowledge from that. As one example, journalist Vanessa Schneider, who's our geomedia lead, likes to talk about space journalism or space data journalism. Journalists are now finding that there are interesting stories to report from these data sets, and in fact, from the Oxford accessibility map data, Washington Post figured out what is the most remote place in the US. I forget what state it was in, but you can see their map. Last year, we talked about the early stages of this project to predict the risk of malaria outbreaks weeks in advance, to be able to plan intervention by clinicians, or where bed nets should be distributed, where spraying should be done, by looking at environmental factors that affect the hatching of mosquitoes. You actually can predict. And the map on the left is what it was the current map for Swaziland of where there was malaria risk. The entire red area, which is more than half the country, was considered to be at risk of malaria. But while true, it's not very actionable, right? It doesn't guide decisions. The map on the right is the more near real time generated from Earth Engine, looking at hotspots of where there actually would be higher risk, as you can see in red. They're calling this precision epidemiology. So this is UC San Francisco. After they established this actually worked, it's now launched as an operational application. It's called Disarm. It's now operating in 4 different countries in Africa, and they're looking at scaling it to some additional vector-borne diseases. So that's been exciting to see. We talked about Matt Hansen Global Forest Change. That was an annual analysis that he did, but can you see the pink lines sneaking through this imagery? Matt Hansen and his team have now developed a weekly Landsat-based detection of forest change. So they call it sort of the just-in-time Landsat alert. And this is quite important because if you do analysis once a year, it's kind of, you know, there's an epitaph for something, but it's too late to do anything about it. But by doing this weekly, you can have more impact. It's a real cat and mouse game now in the Amazon, and I'm not an expert, but we have some experts here from Brazil. Sometimes now the loggers actually log in the rainy season, even though that's not so convenient, but they know they can't be seen from space with optical imagery. But SAR sensors can peer through the clouds, and the NGO, Instituto Socioambiental, used Earth Engine to look at Sentinel-1 SAR data, and you see that line where they detected there seemed to be some kind of change happening they thought it must be a bug in their algorithm because it was in the middle of nowhere. And normally, you have logging happening when there's near to a road. But finally, they sent a plane, and sure enough, they had detected an illegal mining site that had just sprung up. And with that data, they were able to provide that information to authorities and get that shut down. So yay for radar data. If you're interested to learn more, they published a blog post in our Medium blog, Chasing Deforestation Through the Clouds. And just a few months ago, they've now launched an operational application powered by Earth Engine called SIRAD-X, and they're producing monthly bulletins for enforcement and so on. So it's been really exciting to see how quickly these can go from would something work to yes, it works to okay, now let's build something that actual decision makers can use. FAO, we have some folks from FAO. The Forest Resource Assessment, this is something that many countries of the world do to report on the state of their forests. And they're now using Earth Engine as of earlier this year in an agreement that is going to be part of Sustainable Development Goal reporting on the state of the world's forests. A few more of these. Remap is, this just launched recently. This is looking at conservation assessment for against like the IUCN Red List. I'm going to go more quickly here. Mop Biomas. This is an amazing project doing annual land cover and land use change monitoring in Brazil 10 times faster than ever possible before. And now it's scaling to 11 other countries in South America. They've done amazing collaborative capabilities. They have scientists and practitioners from all over the country working, collaborating online. There's a number of agriculture applications. This is one for doing crop yield estimating, crop health, crop yield. And finally, example, Global, Resource Watch was just launched by World Resources Institute. This is trying to look at many different resources in the world, forests, water, and so on. And a lot of that is powered under the covers by Earth Engine. So it's been really an exciting year to see this. Feels like an inflection point of people making science and applications that matter. The community is fantastic. It's been growing kind of exponentially. The graph on the right is the one that we care more about, and that is people actively using the platform to do real work. This one's also exciting, which is the publications that are coming out powered by Earth Engine. To be clear, this is Google Scholar index of the term Google Earth Engine. So a lot of those are serious studies that were fundamentally powered by Earth Engine. Some of them may be casual mentions, but it does give you a sense of where things are going. There are two journals, Journal of Remote Sensing of the Environment and the Journal Remote Sensing, both created special issues dedicated to Google Earth Engine applications. The submission deadline for both of those just passed, but I'm just curious, how many people submitted? Did anybody here submit? Okay, yes, good luck. We're not picking any favorites, but may the force be with you. Okay. All right, so the last section here is what's new. As I said, we like to use this event as a cattle prod? No, as an incentive to get some new stuff out of the oven and in your hands. And so you are seeing this for the first time. Everyone's seeing this for the first time. And what we have linked here are the talks at this event that will be focusing on this. So if you're interested in these areas, make sure you go to these talks. A big focal area for us is integration with Google Cloud Platform. We have found, and many of you in this room are in this category, people have hybrid workflows where they want to use Earth Engine for some stuff, they want to use Cloud Platform for some stuff, and they want to be able to, let's say, talk to our data catalog from, let's say, Compute Engine. And so we have a new API coming out that makes that easy and is in a cloud-friendly form. If you want to learn more about that, go to that talk. Some of these are a little specific, but I think they are heavily requested by the community. So we have this whole area we call like interoperability and exporting. In other words, we don't assume that you'll do everything you ever wanted to in Earth Engine. There may be things you do in other tools and bring in, or you may use Earth Engine for some things and then export out and bring it into other tools. We want to facilitate that. So we just launched, we're launching exporting of a table to an asset. That allows you to keep using it in Earth Engine and exporting it as a shapefile. So that's out. And then there's a new format that is gaining traction in the open data community called Cloud Optimized GeoTIFFs. You can now export your rasters as a Cloud Optimized GeoTIFF. Many of you won't know what it means, but for those of you who do, you'll be happy. Okay. And this is Conservation International arranged to create a QGIS plugin. So from your desktop, you can talk to Earth Engine. And they're doing some amazing conservation-related work with that for people that are in the desktop environment of QGIS. And again, Dave Thau will be doing a session on that. We launched the ability to publish from Earth Engine to the new Google Earth. Yes. And she said, woo, because no. Our first example of this was with NASA and being able to publish the Earth Lights at Night data set as an overlay in Google Earth and with stories and so on. It's turned out to be incredibly popular in Google Earth. And so if you are trying to reach an audience like that, this is a very useful capability now. You can view your results in 3D and so on. The person who's going to be teaching you about this is Chris Herwig. He has an odd idea of what kind of data you might want to publish in Google Earth. His dog. OK. So don't get too hung up on that this is what we expect you to publish. All right. Another really key area of focus for us is the integration with Tensorflow deep learning. Google has arguably the most advanced AI machine learning capabilities on the planet. We think it's a very fertile area for advancing in the field of remote sensing, to be able to bring together Earth Engine data and capabilities with that TensorFlow deep learning in a bidirectional way. And I won't say more about that, but if you're interested in deep learning, and I think everyone should be, this is a session to go here, and I think some of these are going to be given more than once. Maybe, it's like they're all your children and you don't want to have favorites, but I have to say, this is my favorite, launch. And to be clear, we are launching it only to you so far. So how many of you have used what we call maps with knobs or the user interface API to put a bit of a user interface on a script? Yes, OK. And of those, how many of you have wished you could share it with somebody who is not an Earth Engine user? Yes. Well, now you can, right? Yeah. I don't know why it took us this long. We looked at our notes from 2010 about our vision, and this was in there. Anyway, it's harder than you might think, but you can now, you'll be able to publish your applications. You'll get your own URL, and you can share this with anyone. We're only rolling it out initially to people at the summit. We want you to pound on it and test it, and once we're sure it's all working well, we'll launch it officially everywhere. You should absolutely go hear Lauren's talk. She's been the lead on this. Go, Lauren. All right, we're at the end of my session. We made something special for you guys, because we're nerds, right? And our idea of special may not be, it's not a cake or anything like that. It's a techie thing. But so this is one way to look at who's here, right? It's a chloropleth. It aggregates by country. Okay, that's fine. We were like, what could we do with Earth Engine? We know, 200 people here. You're coming from all over the world. We've all gathered in Dublin. What could we do with Earth Engine that would be a little more interesting to show our community coming together? So here we are. This is an anatomically correct visualization. In other words, this isn't hypothetical. Each one of those origins is one of you. Each one of those streaming paths of light is one of you. So find yourself in there. And this is how we view you. We view you guys as streaming paths of light who are going to do amazing things with our technology to make the world a better place. And have a great summit.
All right, thank you, Rebecca. As usual, we have a whole bonanza of courses for you guys this time around. And the descriptions are on the website, but at this point, I'd like to invite all the presenters, internal and external, up to the stage here. So we can give a brief pitch for what these classes are about.